Now we're going to talk about Chapter 6 topics, which talk about computer architecture. So computer architecture is the instruction set architecture, or ISA, that we're going to use for a processor. And the instruction set architecture consists of the assembly language. So this is the human readable format of these kind of very small instructions like add and subtract. And then we convert those into machine language, and that's just the ones and zeros, the encoding of these assembly language instructions. And we'll talk about programming, how we can build or write high-level constructs using assembly language, and how we address operands. And finally, we're going to put it all together by compiling, assembling, and loading a program into our machine, and the catch-all of odds and ends. So here we are in our thread of abstraction here. We're jumped up to architecture. We were down talking about in the previous chapters digital circuits and logic circuits. Now we jump up a higher level of abstraction to architecture, and keeping in mind our programs or application software and a little bit of operating systems. And then in Chapter 7, we'll start talking about how we actually build a machine, a processor, to perform these instructions. And that's the microarchitecture. So here we've jumped up these levels of abstraction to architecture, but remember that microarchitecture is the actual kind of building blocks, the digital building blocks we put together to implement these instructions. And some people tend to conflate these two, architecture and microarchitecture. And architecture can have many different microarchitectures or implementations, as we'll see in Chapter 7. So assembly language is the language that we use to command a computer. So these are instructions, and assembly language is the human readable format, and machine language is how we encode that human readable format into ones and zeros. And we'll talk about the RISC-V architecture, which was developed by Kristya Asanovich and David Patterson and their colleagues at UC Berkeley in 2010, and its development is actually still ongoing. And it's the first widely accepted open source computer architecture. And the reason it's called RISC-V is because it's the 5th RISC architecture developed at Berkeley. And once you've learned one architecture, it's much easier to learn others. So again, Kristya Asanovich is a professor of computer science at Berkeley, and he developed RISC-V during one summer. Well, it started during one summer, and has now become kind of a global community of developers. And he's the chairman of the board of the RISC-V Foundation, now called RISC-V International. And he is the co-founder of Sci-Fi, which is a company that commercializes and develops RISC-V tools and devices. David Patterson is a professor of computer science, also at Berkeley, and he co-invented RISC, the reduced instruction set computer, so a computer with a small number of instructions, or a reduced instruction set, with John Hennessy in the 1980s, and he's a founding member of the RISC-V team. So it's been many years of RISC development for him. And he, along with John Hennessy, was given the Turing Award, which is the highest award given in the field of computing for pioneering a quantitative approach to designing and evaluating computer architectures. So John Hennessy, he was the president of Stanford for a very long time, 2000 to 2016, and a professor of electrical engineering and computer science there since 1977. And again, he co-invented RISC with David Patterson in the 80s, and was awarded the Turing Award with David Patterson, as I mentioned. So we're going to use these underlying design principles that were articulated by Hennessy and Patterson in designing architectures. And actually, these design principles are useful for designing any kind of complex system. So simplicity favors regularity. So if we have a simple design or a regular design, then that will support a simple implementation. And that helps in both understanding, building, and debugging the system. Make the common case fast. Third principle is smaller is faster. And the fourth one is the catch-all of, well, sometimes we're going to violate these above 3 principles because good design demands good compromises. So that's the kind of caveat of, well, sometimes we won't do those top 3 things.